Welcome to homework.
Okay, we've got a few different sets of molecules, and we have to determine if they're the same constitutional isomers or different compounds. Now, I'll let you in on a secret. If you have some number of carbons in a ring, say 6 carbons, and you put them in a ring, and then you have 6 carbons in a chain, they will have a different number of hydrogens. So the rule for chains is that it will be n carbons and then 2 times n plus 2 for a chain. Whereas for a ring, if you have n carbons, it'll be for the number of hydrogens 2 times n, no plus 2. Right, so I can predict pretty much right away that the formula for the 6 carbon ring is going to be C6H 2 times 6 or C6H12, whereas for the chain, I'll have C6H 2 times 6 plus 2 or C6H14. So at a glance, I can tell that these would be not isomers of each other because they contain different numbers of hydrogens. The same is true, losing 2 hydrogens for a ring for double bonds. That is, if I put a double bond here, I know that it will not be an isomer of the straight chain without a double bond. And the formula, every time you add a double bond or a ring, you lose 2 hydrogens. Add double bond or ring, lose 2 hydrogens. Okay, so that's the rule. So when we look at question A here, and we see a 5-carbon ring versus a 5-carbon chain, I know that they cannot be isomers. They are different compounds. And that's because I know the formula for this is C5H10, and the formula here is C5H12. If they contain different numbers of atoms, they cannot be isomers. Okay, next up, we have a 4-carbon chain with chlorine on the end, and then we have a 3-carbon chain with chlorine on one end and a second methyl on the middle carbon. And the question is, are these isomers? And the answer is, if I say 1, 2, 3, 4 carbons, and I see 1, 2, 3, 4 carbons here, and we haven't added any double bonds or rings, then I know they have the exact same formula. It doesn't matter how you've rearranged any of the connections so long as you haven't added any double bonds or rings. If they contain the same number of carbons and the same number of chlorines, they must contain the same number of hydrogens. In fact, the formula for a monochlorinated alkane would just be the same as with the with the plain alkane, but you lose 1 hydrogen and gain 1 chlorine. So I can predict that the formula for this compound would be C4H, and then I would use my 2n plus 2. So that would be 10, but I've lost 1 to replace with the chlorine, so it's going to be H9Cl, and the same is true here. This will be C4H9Cl. You can check for yourself by adding in all the hydrogens that aren't drawn so that every carbon has 4 bonds. And you will see that there are, in fact, 9 of them. And you may see why it is that when you add a chlorine, you lose a hydrogen for the same reason. Okay, let's look at the next example. We have a 4-carbon chain with fluorine on either end. Versus a 1, 2, 3, 4 carbon chain. Again, with fluorine on either end, it's just been drawn slightly differently. Right. And so for that reason, we can just immediately tell that this is the same molecule. There's really been nothing changed except for the orientation that they drew the fluorines. To more accurately match it, they drew it like this. And then this, right? Very clearly the same, though. Rotating around the bonds is free and doesn't change anything. Okay, final question. We have a methyl group, a carbon that's doubly bound to oxygen, and then a methyl group on the other side. And for the next molecule, we have a 3-carbon chain with a double bond on the end and an OH group also on the end. And the question is, are these isomers? And so I would say to you again, because these contain the same number of carbons, 1, 2, 3 carbons, 1, 2, 3 carbons, and because they each contain one oxygen, and they each contain the same number of double bonds, a single double bond, then in fact, we do know that they should have the same molecular formula. In fact, since I know it's C3, and then I know that it's got a single double bond, that we should have 2N hydrogens, or 6, except for we've got an oxygen, so we have to lose one. So we say, oxygens do not take the place of hydrogens. So we have C3H6O. Yeah, chlorines and fluorines will remove a hydrogen when you add one, but oxygens do not change the number of hydrogens that you should expect to see. So this would be C3H6O. Likewise, this would also be C3H6O, and we can verify by drawing in the implied hydrogens. Hydrogen, 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 hydrogen. And we could do the same thing here. 1 hydrogen here, 1 hydrogen here, and 3 on the end of the methyl group. Remembering to include the 1 on the oxygen, we see 1, 2, 3, 4, 5, 6 hydrogens, and 1, 2, 3 carbons and 1 oxygen. Same exact molecular formula, so these must be structural isomers or constitutional isomers.